Hi everybody. I want to spend this video going through problem 553 from the David Klein Organic Chemistry 3rd edition textbook, focusing on identifying the relationship between two compounds when they're displayed as the Fischer projection. So in this problem we have two different pairs of molecules. Both of them are displayed in the Fischer projection, and remember the Fischer projection uses horizontal and vertical lines displayed at right angles to each other to indicate carbon centers. And what we know is that anything drawn on a horizontal line is coming towards us, whereas anything drawn on a vertical line is going away from us. And it looks a little bit strange when you draw it in this way that I just did on the right, because if you think too hard about it, you would realize that the vertical direction, this molecule is going to be coiled on itself, bent back like a scorpion's tail or something. So it's a bit of an unusual way to think about progressive stereocenters next to one another, because we know that's not the lowest energy orientation, but what it is a convenient way to draw molecules that are fairly complex, like the molecules shown here, or in biochemistry, like some fairly complicated sugars and things like that. So when we want to determine the relationship between two compounds, we first want to think about what has changed at each stereocenter. So how many stereocenters are there, and what has changed at each one, or which ones have changed? When we look at the first pair of molecules in problem E, we see here, we can zoom in a little bit, that there are three stereocenters here at carbon 2, carbon 3, and carbon 4. We also notice that the molecule is symmetrical. Both the top and the bottom terminate in methyl groups, and so we have to be careful here on this one. But what we're going to see when we go through this is that the stereocenters do in fact change in each case. And so when we look at it and we say, just comparing here at carbon 2, we had the hydroxide drawn to the right, and now it's to the left. So we could say that this one has been reversed. We'd also say the same thing about the second one and the same thing about the third one, as those hydroxide groups appear to have been moved to the other side of the molecule. And we would be right in saying that all three stereocenters have in fact mirrored if the molecule wasn't symmetrical. Now, because the molecule is symmetrical, we can think about redrawing this one. And all I'm going to do is rotate this by 180 degrees, top to bottom. Remember, Fischer projections can be rotated 180 degrees on the page without changing their meaning. They cannot be rotated in any other way, because remember, those sideways horizontal bonds are coming towards us. If we turn the molecule 90 degrees, we've changed the meaning of those bonds. So if we rotate this 180 degrees, we would draw that this molecule still has the same structure like this. And I'm going to highlight here this methyl group is now the methyl group on the bottom. Right, I've rotated it 180 degrees in sort of the top to bottom direction. That means that the OH group that I've underlined here in blue that was on carbon 2, we may as well keep that as carbon 2, but now carbon 2 is down here. That OH group now, after the rotation, would be drawn over here to the left, and the hydrogen that went with it. The OH group in the middle on carbon 3 that used to be drawn to the left now has rotated over to the right. And the OH group that was on carbon 4, I'll pick a different color for that here, is now going to be drawn up and to the left like that. And of course we have our methyl group on that end. Okay, my color coding here is just meant to give you some highlights to see what we've done to the molecule. Okay. Now that we've rotated it 180 degrees, we can compare it to the other molecule in the pair, and we see that they are in fact identical. So when it says identify the relationship, these ones are identical to one another. Contrast that to the molecules shown in part F. Now in part F we see that we have the two Fischer projections. We also can see now that it's not symmetrical. This is drawn with an ethyl group at the top and a methyl group at the bottom. So we won't have that same curveball being thrown at us about turning it 180 degrees and having the same molecule show up. So now we want to look at the two and say, yes, we do have the same orientation here, ethyl at the top, methyl at the bottom. Now we look at the stereocenters. I can see that the OH group on carbon, well, 1, 2, I guess it would be numbered from the bottom, wouldn't it, guys? So 1, 2, 3, 4, and ethyl would be 5 and 6. So the topmost OH group on carbon 4 has been rotated to the other side, has been mirrored, right? And so this one, I do have a mirroring that's happened. The one in the middle, likewise, has undergone a mirroring. And the one on the bottom, likewise, has undergone a mirroring. Now, since all three of those have the mirror image, this represents a pair of enantiomers. Remember, enantiomers means that we have every single stereocenter in the molecule has a mirrored configuration. So if I have 2 stereocenters, both of them are mirrored. If I have 15 stereocenters, all 15 of them are mirrored. Those are enantiomers. Anything short of that would be called a diastereomer. And so we'll take a minute here just to draw that out. If a problem, different problem, said, diastereomer. Yeah, that's right. If a problem asked us to draw a diastereomer of one of these molecules, all we would be doing is drawing our backbone, putting everything on the backbone in the same place, but then switching only some of the stereocenters. So maybe I choose to draw this one where I have mirrored only the stereocenter drawn at the bottom on carbon 2. Maybe I decided I wanted to draw another one. And maybe in this case, I want to mirror the middle. Oh, heck, maybe I'll mirror both of these. Okay. Any combination of these are going to be diastereomers of the molecules drawn up above. So I have a pair of enantiomers drawn at the top, represented there in blue, and then I can draw a number of different diastereomers. When a problem is going to ask me sometimes how many stereoisomers are possible, we're going to take into account that every single stereocenter has 2 possible configurations, either R or S. And so the formula for the number of stereocenters that are possible is going to be 2 raised to the n power, where n is the number of stereocenters. And so for this particular molecule with 3 stereocenters, I would have 2 to the 3rd power, which is 8 possible stereocenters. 8 possible stereoisomers. 3 stereocenters, 2 to the 3rd power is 8 stereoisomers. I could draw that as 4 pairs of enantiomers. So the pair I showed in blue and 6 other structures that would represent 3 perfect mirror image sets. So it takes a little bit of practice in identifying relationships between compounds regardless of their format, but especially for Fischer projections. So with that, practice makes perfect. Try a lot of problems here and hone your skills. Good luck.